In our previous module, we have seen that when the sample size is fixed, it is not possible to minimize both the error probabilities at the same time. Actually, a test that minimizes the probability of type 1 error maximizes the probability of type 2 error. To overcome this difficulty, the probability of type 1 error is kept fixed at a level alpha, and subject to that constraint, the probability of type 2 error is minimized. In the present module, we first introduced the concept of level of significance of a test, and then we shall define the size of a test. In case of discrete distribution, the actual size is very difficult to achieve. So here we shall introduce the idea of a randomized test. And finally, we shall discuss the linear combination of two randomized tests or two tests, which is also a level alpha test, and we shall introduce the concept of p-value of the test. Some examples are discussed in this connection. In the previous module, we have seen that when the sample size is fixed, it is not possible to minimize both the error probabilities at the same time. A test that minimizes the probability of type 1 error in fact maximizes the probability of type 2 error. To overcome this problem, Neyman and Pearson suggested that one may select a suitable upper bound for the probability of type 1 error and consider only those critical regions for which the probability of type 1 error does not exceed the selected upper bound. Secondly, among all these critical regions, select the one for which probability of type 2 error is the smallest. This upper bound is called the level of significance of the test. Now we shall define the level of significance. A test with critical region omega is called a level alpha test, where alpha belonging to the interval 0-1 if probability x belongs to omega given theta belongs to script theta h less than equals to alpha, where alpha belongs to 0-1 is a pre-assigned quantity and it is called the level of significance of the test. Note that a level alpha test is also a level alpha naught test for alpha less than alpha naught less than alpha naught less than 1. Here alpha and alpha naught are the upper bounds of the set of the probability of type 1 errors. It is quite natural to look for the least upper bound of the set of all probability of type 1 errors. This is called the size of the test. Now we define the size of a test. A test with critical region omega is called a size alpha test, where alpha belonging to the interval 0-1 if the supremum over theta belongs to script theta h, probability x belongs to omega, that is the probability of type 1 error, is equals to alpha. Note that a size alpha test is also a level alpha test. A test with level alpha is easily attainable whereas it is not easy to attain the exact size alpha test when the underlying distribution is discrete. It is clear from the following example. Let theta be the probability of getting a head in a single toss of a coin. For testing h naught or h, theta equals to half against ha, theta greater than half. Suppose the coin is tossed 5 times and h is rejected. If the observed value of x is greater than c, where x denotes the number of heads in 5 tosses of the coin and c greater than 0 is a constant. Now under h, x follows binomial distribution with parameter 5, half. Then from the table of binomial probabilities or by computing we get probability under h, x greater than 3 is equals to 0.1875, but probability under h, x greater than 4 is equals to 0.03125, which is less than alpha if we set alpha equals to 0.05. Therefore, if we take c equals to 4, then the test is a level 0.05 test, but it is not a size 0.05 test. To attain the exact size, we use the randomization technique. Now we define a randomized test, which is also called a probabilistic test. It consists of determining a real valued function phi x such that phi x is a mapping from script x to 0 1, that is from sample space to 0 1, or 0 less than equals to phi x less than equals to 1 for all x, such that whenever x equal to small x is observed, a test is rejected or accepted according as success or failure is occurred. By performing a Bernoulli trial with probability of success equal to phi x. Here phi is called test function or the critical function. Note that a non-randomized test can be looked upon as a special case of a randomized test, because in case of a non-randomized test, omega is equals to the set of all x for which phi x equals to 1. This is the critical region, and script x minus omega is the set of all x for which phi x equals to 0. Therefore, in case of a non-randomized test, the function phi x can take either the value 0 or the value 1. In general, a randomized test is of the following form. Phi x equals to 1 if the sample point x belongs to a region E1, say, equals to gamma if x belongs to E2, and equals to 0 if x belongs to E3, where gamma is a constant lying between 0 and 1. Here EIs are mutually disjoint subsets of script x with E1 union E2 union E3 equals to script x. The constant gamma is so chosen to satisfy the size condition. In terms of the test statistic Tx, a two-sided or two-tailed randomized test is given by phi x equals to 1 if Tx less than equals to some constant Cl, or T Tx greater than equals to some constant Cu equals to 0 if Tx lies between Cl to Cu. With randomization at Tx equals to Cl or Tx equals to Cu. Note that in the region E2, if a sample point falls in the region E2, then we perform a random experiment with probability of success gamma, and if success appears, we reject H0, otherwise accept. Now, in the above example, if we want to get an exact size 0.05 test, then we set C equals to 4. Now, to determine gamma, we use the size condition. That is, probability under H x greater than 4 plus gamma times probability under H x equals to 4 is equals to 0.05. After some calculations, we get gamma equals to 0.12. Therefore, the test can be interpreted as follows. If the observed value of x is greater than 4, that is the number of success is greater than 4, we reject H0. But if the number of success is less than 4, we accept H0. But if the number of success is equals to 4, we perform a random experiment with probability of success 0.12. That is, we select a random number from the interval 0, 1, and if the selected number is less than 0.12, we reject H0, otherwise we accept H0. Actually, the randomization is done to achieve the exact size, but as a result of randomization, the power of the test also increases. Now, we define the power function of a randomized test in terms of the critical function. We have seen that a randomized test phi x is the probability of rejection of H when x equal to x is observed, and hence the unconditional probability of rejection of H is integral over script x phi x into px theta dx, where px theta is the joint distribution of x, and therefore it is equals to the expected value of phi x under theta, where theta belongs to script theta. Therefore, the probability of type 1 error of a randomized test is given by expectation of phi x under theta, where theta belongs to script theta h, and the size of a randomized test phi x is defined as the supremum value of expectation of phi x under theta when theta belongs to script theta h. It is clear that when h is simple, that is script theta h equals to theta naught, then there is no need of taking the supremum, and the size of the test is equals to expectation under theta naught phi x. Similarly, we can define the probability of type 2 error. This is equals to expectation under theta 1 minus phi x, where theta belongs to script theta ha, and this is actually the 1 minus power at the point theta, where theta belongs to script theta HA. Thus, the power function of the test phi is defined by beta phi theta is equals to expectation under theta phi x, where theta belongs to script theta. Phi is a level alpha test if expectation under theta phi x is less than equals to alpha for all theta belongs to script theta h. And if it is a size alpha test, then supremum over theta belongs to script theta h. Expectation of phi x under theta is less than equals to alpha. Now we are going to discuss a very interesting result on critical function. Let phi 1 and phi 2 be two level alpha tests for testing H against HA. Then any convex combination of phi 1 and phi 2 is also a level alpha test for testing H against HA. To prove the result, we take a constant lambda in the interval 0, 1, and we set a function phi x equals to lambda into phi 1x plus 1 minus lambda into phi 2x. Actually, it is a convex combination of phi 1x and phi 2x. Here phi is a mapping from script x to 0, 1 because both phi 1 and phi 2 are mappings of script x to 0, 1. Moreover, expectation of phi x under theta is equals to lambda into expectation of phi 1x under theta plus 1 minus lambda into expectation of phi 2x under theta, which is less than equals to lambda into alpha plus 1 minus lambda into alpha for all theta belongs to script theta h. This is so because here both phi 1x and phi 2x are level alpha test, and therefore we get expectation of phi x under theta less than equals to alpha for all theta belongs to script theta h, and hence phi x is also a level alpha test for testing H against HA. Now we define a very important concept which is called the p-value of a test. Instead of fixing the level of significance alpha, one can obtain the level actually obtained by a test. This is called the p-value of the test. If the test is a upper tail test based on capital Tx, then the p-value is defined by L plus x, which is equals to probability under theta. Tx is greater than equals to the observed value of Tx. But if the test is a lower tail test based on the statistic capital Tx, then the p-value is defined by L minus x, which is equals to probability under theta, Tx less than equals to the observed value. Both the probabilities are calculated under H, that is under the null hypothesis. The test is a both-tailed test based on a statistic Tx, then the p-value is defined as the twice minimum of L plus x and L minus x for all theta belongs to script theta h, provided the distribution of Tx remains same over the null hypothetical set script theta h. If we assume that the distribution of Tx is continuous, then L plus x plus L minus x equals to 1. Moreover, under theta belongs to script theta h, the distribution of L plus x and L minus x are rectangular 0, 1. Actually, L plus x is equals to 1 minus capital F of Tx, where capital F being the distribution function of T, and L minus x is equals to capital F of Tx. Smaller the value of L plus or L minus gives stronger evidence in favor of the rejection of H or against H, and we reject H if the p-value is less than alpha, otherwise we accept it. When the distribution of Tx is discrete, we can modify our level actually attained by defining the p-values as follows. If the test is a right-tailed test, then the p-value is defined by L plus x is equals to probability under theta Tx greater than the observed value plus half times probability under theta Tx is equals to the observed value. And if the test is a left-tailed test, then we can define the p-value as L minus x equals to probability under theta Tx is less than the observed value plus half times probability under theta Tx is equals to the observed value. For all theta belongs to script theta h, that is, all the probabilities are calculated under h naught. Here L plus x and L minus x are approximately rectangular 0, 1 under H. It is interesting to check that under continuous setup, the distribution of Lx, which is the twice minimum of L plus x and L minus x, is also follows rectangular 0, 1 whenever theta belongs to script theta h. Let us close our discussion with some examples. First, we consider a random sample x1, x2 up to xn of size n drawn from normal mu, sigma square population. Suppose we are interested in testing h mu equals to 0 versus HA mu greater than 0. If the variance is known, say sigma equals to 1, then here we use the test statistic capital Tx is equals to root n into x bar divided by sigma. Actually here x bar is sufficient for mu when sigma is known, and therefore it is reasonable to use a test statistic by a function of x bar. Now under h naught, Tx follows standard normal distribution, and here we reject h naught if the observed value of Tx is too large. When sigma is unknown, here we use the test statistic Tx equals to root n into x bar divided by s, where s is defined as the sample standard deviation, which is the square root of 1 by n minus 1 summation over I from 1 to n xi minus x bar square. And under h naught, t follows student t distribution with n-1 degrees of freedom, and here we also use a right-tailed test. Note that the distribution of Tx remains same for all values of theta under the null hypothetical set. Next we consider a test for the population SD. Suppose we want to test H sigma equals to 1 versus H A sigma greater than 1. Now if mu is known, then here we use the test statistic capital Tx equals to summation over I from 1 to n xi minus mu whole square, which follows chi-square distribution with n degrees of freedom under the null hypothesis H. But if mu is unknown, then we cannot use the above test statistic. In that case, we replace mu by x bar and we modify our test statistic as Tx equals to summation over I from 1 to n xi minus x bar whole square, which follows chi-square distribution with n-1 degrees of freedom under the null hypothesis. In both the cases, we use a right-tailed test for testing H against HA. In the present lecture, we have seen that though randomization is used to achieve the exact size, but due to randomization, the power of the test also increases. Therefore, randomization plays a very important role in the test of significance. And we have seen that a non-randomized test is actually a particular case of a randomized test. In the lecture, we have seen that the power function of a randomized test can be expressed as an expectation, and we have seen that the p-value plays a very important role in the theory of testing of hypotheses. In case of continuous distribution, the distribution of p-value is rectangular 0, 1, but when the distribution is discrete, it can be approximated by a rectangular 0, 1 distribution.